Okay, today the next speaker today, this is Boyan Kostadinov. The title is Noncommutative Invariants of Dihedral Groups, please.
Thank you. So before I say anything else, I would like to quickly introduce myself. Just a second. Yeah. I would quickly like to introduce myself since I assume that most of you don't know me. My name is Boyan, as Vesselin Drensky said, and in the last few months I have been doing a postdoc here at the Institute of Mathematics and Informatics. I have two advisors. One of them is Vesselin Drensky, and the other one is Vladimir Gudinov. Today I will try and present to you the results that we have obtained together with Vesselin Drensky. So yeah, let me start. This is the quick overview of how the presentation is structured. My plan is to first start with the definitions. Then, well, I will not probably discuss all of them since I assume that most of the definitions are known to any of you. And then I will say a few words about the introduction of the problem that we consider. In the third section, we will have a look at the preliminaries. These are more like classical and well-known results that we use in our work. And as you can see, the last section is devoted to the results that we have obtained. Here, we start with the definition of an algebra. I don't think there's much need to discuss it. The only thing that I would like to point is that usually when we say algebra, we don't expect the unitary elements to be part of the algebra. And also we don't expect, for example, the algebra to be associative. This is something that we explicitly require, as we will see in the next slides. Next, we stop at the definitions of subalgebra and ideals, left or right. Again, I think this is something that we don't need to discuss in details. Here, as I said a couple of slides ago, we say what an associative and the commutative algebra is. I think this is also pretty straightforward. In relation to a algebra, I would like to say how it's defined. It's defined by fulfilling those two identities here, those two relations. The first one is the anti-commutative form, and the second one is the so-called and probably well-known Jacobi identity. Let me say a few words about the third definition, which relates to the free algebras generated by a certain set. Let us have a class of algebras, and let's pick an algebra F, which is generated by a set X. We say that this algebra F is a free algebra in the class P, and it is fully generated by a set X. This is true if for any algebra, if for any algebra that we pick at random from the variety B, every mapping from the generating set to the algebra of our choice R can be extended to a homomorphism from the algebra F to the random algebra we have chosen. The next one, the next definition relates to the notion of module and representation. Let me again say a couple of words about this definition. If we have a vector space M and associative algebra R, and if we have an algebra homomorphism ρ that maps the algebra R to the algebra of all endomorphisms from M to M over the field K, then we say that the homomorphism ρ is a representation of the associative algebra in the vector space M. And we also say that M is an R module. The module could be left or right, depending on which side we do the multiplication or the operation that we use. The next definition is about varieties. Let me again say quickly a few words. If we have a set of polynomials f sub I, which depend on those variables x sub 1 to x sub n sub I, then we say that sorry, if we have a set of polynomials in the, I missed that, it's in the free associative algebra. The class. Okay. I thought someone is experiencing a problem with the connection and would like to. Okay. So the class B of all associative algebras that satisfy those identities here, f sub I equal to 0. This is called a variety, and this variety is generated by the system of the polynomial identities f sub I. A variety W is said to be a subvariety if it is a subset of the variety B. I hope this is not too boring for you because, as I said, probably you know it, but I think it's good to at least mention them before we continue. The next definition is the definition of Hilbert series, or so-called, also called the Poincare series. The formal definition of Hilbert series is summation over all i's which are greater than or equal to 0, multiplying the dimension of each subspace Wi by t to the power of I. What is Wi? Well, Wi is a subspace of W such that the space W is a graded vector space, which means that it can be represented as a direct sum of its subspaces Wi. And one more thing that is good to mention here is that the dimension of each subspace Wi is a finite number. The notion of commutator ideal is also something that we quite commonly use in our work. So in brief, a commutator ideal denoted by f prime of the algebra F is given in this form, or more specifically, its elements are represented as a sum of terms of this form. Here we have an element that belongs to the field that we consider K. On the left side, we have a monomial that depends on x sub 1 to x sub n. On the right, we have similar monomial, and in the middle, we have the usual commutator that we know, the Lie commutator. And each of x sub 1 to x sub n are elements of the algebra.
You should say that this is in the case of the metabelian, because in the general case, this thing may be x, the beginning in the end.
Okay, so yeah, my mistake. So I have missed this in the descriptions. Okay, so now we jump into the introduction, into the second section, the introduction. Here, in general, what we do is over the field of complex numbers C. Nevertheless, the results can be restated for any field K of characteristic 0. When we speak about the classical commutative invariant theory, the general linear group acts on the d-dimensional complex vector space V sub d with a certain basis. And this action, in turn, induces an action on the algebra of polynomials denoted by C of x sub d. And for a subgroup G, that is a subgroup of the general linear group, the algebra of G invariants, denoted in this way, consists of all polynomials that remain unchanged under the action of the group G. Later, when I say later, I mean a few slides after this, we will see a formal definition of the notion of invariance. So on the other hand, in some of the main branches of the non-commutative invariant theory, we can replace the algebra of polynomials by an algebra that has pretty much the same or similar properties of the same algebra. What's a good option for that, or a good approach? It is if we use a structure or an object that has the same properties. What are the candidates? Well, the candidates could be the associative algebra C of x sub d, the free Lie algebra L sub d, or the degenerated algebra of a certain variety of algebras. So in this case, it is more convenient or more easier if we assume that the general linear group acts directly on the vector space C x sub d with basis x sub d rather than on the vector space V sub d. If we jump back for a moment to the classical invariant theory, this means that the general linear group acts on the symmetric algebra of C x sub d instead of the algebra of polynomial C of x sub d. If we have a variety of unitary associative algebras, which is in this case called P, and this is over a field of characteristic 0, and if A sub d is the relatively free algebra generated by the set x sub d, then the general linear group GL sub d acts on the vector space k x sub d, and this action can be extended on the entire algebra A sub d. How it's extended? It's extended in this way, which means that the element from the general linear group G acts on each of the variables from the polynomial f, and the polynomial f belongs to the algebra A sub d. Here we have, as I said, the formal definition of the notion of invariance, which means that the invariance of the algebra A sub d consists of all polynomials f that belong to the algebra A sub d, such that those polynomials remain the same or remain unchanged under the action of the group element G. The following theorem is important, and we take advantage of it. It says that if we have a variety of unitary and associative algebras, the following two conditions that relate to the variety are equivalent. What are the two conditions? Well, sorry, not condition, but statement. I think it's better if I say it this way. The first statement says that the algebra of invariants is freely generated for every unit subgroup G of the general linear group. And the second statement says that the variety B satisfies this identity here. For, of course, in the cases when n is large enough and when the length of the commutator is also sufficiently large. The definition, probably I should have put this in some of the previous slides, but as I mentioned, the commutator of two elements is the well-known Lie commutator, and it's given in this form as we know it. And the longer commutators are left norm, which means that we can define them in this way for n greater than or equal to 3. The next definitions relate to the metabelian identity, and pretty much they're overlapping, and probably the first one is redundant, but still I thought it's good to at least have it in the presentation. So
the associative case is the product, it's not commutator.
Okay, yeah. So that's a typo. Okay, then I will just say that I will focus on the second definition. So okay, so we say that a Lie algebra is the metabelian variety of a Lie algebra is defined by this polynomial identity, which is actually the metabelian identity. When we speak about metabelian property, we usually refer to a sort of this polynomial here. Okay, the next thing that it's good to mention is the fact that a free metabelian Lie algebra, L sub d, is embedded into the associative algebra A sub d, and when the field of interest is
the first equation is the product of two commutators. It's not the commutator of the commutators. In the associative case.
Okay, so yeah, that's
you should carry this in the slide sometimes.
Yeah, I will just remove it because in any case I think it's redundant.
Okay.
Okay, so in the case when
this is variance of Dihedral. Okay. Sorry.
No, it's fine.
It's okay because I didn't see that second part. It was the algebras. It's okay. It's my fault.
Okay. Yeah. So you mean the associative case? Okay. I think again. Where was I? Yeah, in the cases when we consider the field to be the field of complex numbers, the results of the algebra of invariants of A sub 2 allow us to obtain a minimum set of generators for the invariants of the commutator ideal as a module. So the last one, since we will see it in the next slides. Now we are already in the third section, where, as I said, we use some classical and well-known theorems. The first one is the theorem by Emil-Noether. It's about the fact that the algebra of invariants is finitely generated. And okay, I will skip it because I think it's in any case it's quite ubiquitous and probably everyone knows it. The same thing applies for the second theorem, since this is the famous theorem of Hilbert, the Hilbert. Probably here I will have to say a few more words about the famous Moulin formula. The formula calculates or provides the Hilbert series of the algebra of invariants in a polynomial algebra. The Moulin formula says that this is equal to 1 over the order of the group G multiplied by its summation over each element G of the group G, which is a subgroup of the general linear group. This theorem is generalized by Formanek, and it briefly says, theorem briefly says that the Hilbert series of, again, of algebra of invariants of the algebra S of D equals, again, this term here, multiplied by summation over all elements of the group G of Hilbert series of the algebra. And here we now substitute the variables with the eigenvalues of the respective element of the group G.
There is a zero here.
Yes. Well, if I skip it, don't say it. You can consider the characteristic is zero. The next theorem is the well-known also Chevalier-Chapletot theorem. But before going to the theorem, let me briefly remind what the notion of pseudo-reflection is. If we have an element G from the general linear group, which has finite order, it is called pseudo-reflection if it has an eigenvalue of 1 and its corresponding multiplicity is d minus 1. And there is also another element which has multiplicity 1, and it is an nth root of unity, or simply a root of unity. Respectively, the group G, that's a subgroup of the general linear group, is called reflection if it's generated by reflections. And what the theorem of Chevalier-Chapletot says in brief, it says that again we have two statements that are equal or equivalent. The first one says that the group G is a finite reflection group. The second says that the algebra of polynomials is a free-graded module over the algebra of invariants, and it is finitely generated. It has a finite basis. And the third statement says that the algebra of invariants is generated by, in this case, D, algebraically independent and at the same time homogeneous elements. For the purposes of our work, we need a version of this theorem, which is, let's say, stronger. What the stronger theorem says is that if we have the group G of reflections, and if we also have the algebra of invariants and the polynomial algebra given here, where each f sub I is has a degree this sub I and is homogeneous, then in each of the integers this sub I can be uniquely determined by the group G. On the other hand, the order of the group G is equal to the product of each of these sub i's from I equals from 1 to n, and the number of reflections in the group G is equal to the sum of d sub I minus 1. Okay, now we arrive at the Dihedral groups, also something that we use. So the Dihedral group D sub 2n acts on the two-dimensional real vector space as the group of symmetries of regular and non, and it is generated by either rotation or reflection. Rotation is by angle of 2 pi divided by n, and when we speak about the reflection is in relation to the axis OX. We also use change of variables that was initially introduced by Riemann, and this is the change of variables that we use. In this case, the Dihedral group, this sub 2n, is generated by the rotation law, which acts on u and v in this way, and the reflection tau just simply swaps u and v. Xi is an n root of unity. The following two propositions are important, and yes, we use them a lot. Oh yeah, since they are here, then supposedly we use them. The first proposition said that the algebra of invariants in the polynomial algebra of two variables is generated by u multiplied by v and u to the power n plus v to the power n. The second proposition says that the polynomial algebra CUV is a free module with the following generators. It's 1, u square, etc. I mean, I guess I don't need to read them. The next one, due to the isomorphism of algebras that we see over here, we can state the following corollary. By the way, this is we will see a few slides later. We will see this corollary restated in the case of what we do. So let me go back to the theorem. It says that if we have the Dihedral group D sub 2n that acts on these two polynomial algebras the same way as it acts on this polynomial algebra, then the polynomial algebra of four variables is a free module in the invariants of the algebra of two variables, and it is pretty generated by those four terms, so those four monomials here, under the restriction of A, B, C, and D given here, or the restriction of this is also the restriction of the powers. Okay, so this is I assume that it will be hard for me to explain this, but probably just say that the free metabelian algebra A sub D has basically given by
okay, because when they are monomials, and yeah, not only the element, but x1, a1 times.
You mean this one?
Right, this one.
Yeah, this is a monomial.
No, but this monomial which you have, instead of x1, xd, you have x1, a1, xd, and ad, comma, and then you have this expression. So this is a misprint.
Okay, so okay, yeah.
The first part is the problem. This is the monomial, not this one.
Okay, yeah, I understand. So
you should correct this.
I will change it.
This was the first version of our paper. Is to correct this.
Okay, so my fault again. And the other thing is that it is this equality here that is also satisfied. It refers to, well, the only thing that I would like to note here is that pi and psi are permutations of those sets here. And again, I think it's easier to just point them out rather than say them. Okay, so the next theorem or the next statement, it has two substatements and it relates to the case of two variables, meaning that d equals 2. So in this case, the algebra is the associative algebra S2 has a basis which is given by these terms here. The second substatement says that the commutator ideal is free module which is generated by the commutator between V and U, where the polynomial algebras of two variables act on the commutator ideal by multiplication by U and V from left and right. When we speak about the Lie case, just like in the associative case, the structure of the metabelian algebras is well known, and here is the basis that it refers to the Lie algebra. So what's also worth noting here is that in the case again of two variables, the basis of the algebra L sub 2 consists of those elements here, and the commutator ideal is a free module which is generated again by the commutator between V and U with respect to this action over here, where W is an element of the commutator ideal and F is an element of the polynomial algebra. And we eventually arrive at the final section with the main results. And let me just quickly check how I'm going with the time. Okay, I think I'm fine. In terms of what we do, we use the following isomorphism, which is given in this way, and it maps the commutator ideal to the algebra, to the polynomial algebra of four variables, and how it acts or how it works. So it works in this way. The next proposition is that the Dihedral group acts on the two polynomial algebras in the same way as it acts on the polynomial algebra C UV. This is the statement that we saw a couple of slides ago. Then, in this case, the commutator ideal will be a free module, and it will be generated by those four elements here, with the restriction again on the powers given here. The next statement, or is given here proposition, again has two sub-propositions. The first one says that a polynomial that belongs to the commutator ideal belongs to the invariants of those commutator ideal if and only if it is fixed under the rotations and the reflections that generate the group with these two. These are the same rotation and reflection that we defined earlier. And how put in another way, we have that this relation here is valid. Similarly, the polynomial of 4 variables belongs to the invariants of the polynomial algebra of 4 variables if and only the rotation in the reflection act on this polynomial in this way.
But here you should, this polynomial belongs to the image of the invariant, not to this algebra, because if it belongs to the invariant, then the next one should be plus or minus. So this statement is not for the for this one. This condition here, this is when this thing belongs to the image and not to this one.
Okay. Again, well, I have to change it. Yes. Okay, thank you. So the second position says that the invariants of the commutator ideal are belong to the invariants of the algebra of polynomials in 2 variables, and it's given, and the set of generators is given by those 3 terms over here. Again, with let's say some requirements of the power A. The next result, or the next statement refers again to the invariants of in the associative case, and it says that the algebra of invariants is generated by u times v plus v times u by u to the power n plus v to the power n, and again those 3 elements here, with the requirements of the power a. Next theorem says what the Hilbert series of the algebra of invariants is. Well, it's given by this expression here. I don't think it's necessary to pronounce it. You can see it on your own. Then, yeah, actually, yes, I almost forgot about this. Here we need to make a note or a remark that the generating set of the algebra of invariants is not minimal, since if we take the commutator of the 2 of the generators, first of all, it will have a degree n plus 2, and it can also be expressed as a linear combination of roughly say the other generators. So it's not difficult to prove or to think that if we remove those generators,
only one of them we have to use.
Okay, yeah. Okay, if we remove
one of these generators.
If we remove this generator,
one of these generators.
Okay. Yeah, yes, then we will obtain. Then we will obtain a minimum generating set of algebras of the invariants of the algebra A sub 2. Okay, so now we are already in the case of the algebras. The considerations here are pretty much the same or close. The only difference is that the commutator ideal is a free module which is generated by the commutator V and Q. And therefore we say that we arrive at the following proposition, which says that the commutator ideal is a free module which is generated by this term here and this term here. The next one, which I think it's the last one. Again, it's provided in the form of theorem with 2 sub-theorems. The first theorem says that the invariance of the commutator ideal in the invariance of the algebra of 2 polynomials is free generated, and its generators are given in this form here. Again, just like in the associative case, here the Hilbert series of the algebra of the Hilbert series of the invariants of the Lie algebra LZ2 is given by this expression here. So yeah, this was the last slide on my presentation. I would like to thank you very much for your patience and attention, and yeah, thank you.
I cannot say thank the speaker because I'm a part of this talk, but if you have any questions, you're welcome.
Would you please return to theorems? Theorems, no proposition, theorems.
Okay.
It characterizes.
Did you find any error there? Because Vesselin Drensky already identified a couple.
Yes.
This one.
But yeah, about the 12 or 13 equivalent conditions.
Thank you.
But this is only one of them because this is the result of the effort of maybe 10 authors or more.
Can I ask a question? Yes. For instance, when we have a finite group of the order, some finite order, that acts on a set, and this group is the set, is a group of invariants of this set. There is a connection between the order of the group and the number of invariants. So, for instance, if symmetric groups F3 acts on polynomials with three variables, the order of the group is equal to 6, and the number of invariant elements probably 3. Yes, this is x plus x1 plus x2 plus x3, and x1 multiplied by x2 plus x2 multiplied by x3. 3 and x1, x2, 3, the order 6 of the group, and the number of invariant elements 3, and respectively is the group G 3x on hexagon, the order of this group 12, and after all permutations, we probably all actions of this group, we have 6 hexagons that we numbering sides of this hexagon. In this case, 6 in first example, 6, 3, 6 divided by 2, 3, and for hexagon case, again, 12 and 6 invariant hexagons. And this, so this very simple arithmetic connection between order of the group, of invariant group, and the number of invariant elements. And in general, there are some.
Maybe I explain this. You see, first of all, if you have a finite group which actually the polynomial algebra, the transcendental degree of the algebra invariant, this is the same as the algebra polynomials. This means that the number of the generators of the algebra invariant is the number of the variables or more. For example, if you take a cyclic group of order 3, which act on the polynomial in 2 variables, you can see that the generators are the corresponding number. You can see how many there are. Okay, if you have 3 variables, for example, and the cyclic group of order 3, then the generators are 4, not 3. First of all, the original proof of any algebra, it gives the power of the generators to be equal to the order of the group. 2 weeks ago, there was an examination of one of our PhD students when he explained the original proof. If you want to see, you can simply go back in the whole page of the seminar to see the proof. So in the general case, you have 2 restrictions. One of them is the degree of the generators. This is the order of the group. Usually this is less. And the other is that the number of generators is more or equal to the number of the variables. If the group is generated by reflections, for example, also symmetric groups have this property. The diagram take up this property. Also, there is a list of the groups. If you open the original paper by check on the top, you can see a complete list of all these groups. Then you have exactly such number of the generators as the number of the variables in the polynomial. This is the reflection only when the group is very, very effective. When is the group of central reflections, generator reflections. And also in this case, you know that it was stated in the talk that the product of the degrees of the generators is equal to the order of the group. So here for the diagram group, you have the order is 2n. You have 1 generator of degree 2 and 1 generator of degree n. For the symmetric group, the order of the group is d factorial 1, 2, 3n, and you have the symmetric polynomials of 3rd degree, of 2nd degree, the remaining symmetric functions. They are then 1 of each degree, and the product is again d factorial. So this is the maximum you can get as information. So if there are no more questions, you should stop recording. Okay, and we simply have chat